Hello, my name is Harrison Budker, and today I will be looking at problem number 2 on the Physics 2211 Midterm 1 Spring 2014 exam. The problem states, a block of mass m is connected to two springs. Each spring has a relaxed length L sub O. The spring on the left has a stiffness Ks, and the spring on the right has a stiffness 2Ks. As shown in the diagram, the block is initially released from rest at x equals L sub O divided by 3. The bottom surface supporting the block is frictionless. Part A asks us to choose the block as a system and use the usual axis system with a positive x to the right and positive y running vertically up. Just after you release the block, which external objects are interacting with the chosen system? From looking at the diagram above, you can see that the left and right spring are both applying a force on the block. The Earth is also applying a force on the block as it is applying a gravitational pull, and the bottom surface of the block is applying a force in the plus y direction, combating the force of gravity. Part B asks us, at the instant you release the block, what is the net force on the block? We know that the y component of the net force is 0 because the only forces acting on the block with the y component are the gravitational force and the force from the ground pushing up on the block. These forces cancel each other out because the block is never moving in the positive or negative y direction in this problem, thus making the net force in the y direction 0. Now we have to look at the net force in the x component. These two forces come from the left and right spring. We must use the equation for spring force, which is K sub s times the final length minus the relaxed length times L hat. For the left spring, the L hat vector is -1, 0, 0, because the spring is being elongated, and in the right spring, L hat is -1, 0, 0, because the spring is being compressed. Now we just plug in the final length and the spring stiffness for both springs. Once we do this, all we have to do is add the force from the left spring and the force from the right spring, and we get F net is equal to -K sub s times the relaxed length of the spring, 0, 0. Part C tells us to determine the new velocity of the block a short time delta t after being released. Here delta t should be taken as a given. Your answer must be expressed as a vector. We first must start from Newton's second law, which states the final velocity equals the initial velocity plus F net divided by m times delta t. Since the initial velocity is equal to 0, V final is equal to F net times delta t divided by m, which gives us the vector -K sub s divided by m times the relaxed length of the spring times delta t, 0, 0. Part D then asks us to use our answer from Part C to calculate the new position of the block. To find the final position, we must start from Newton's second law, which states that the final position is equal to the initial position plus V average times delta t. For this problem, we will use final velocity as a good approximation for the average velocity. At this point, all we have to do is plug in. We know that the initial position vector of the block is the relaxed length divided by 3, 0, 0, and we must add that to the average velocity vector, which is just our final velocity vector of -K sub s divided by m times the relaxed length of the spring times delta t, 0, 0, and then times delta t. Thus, the final position vector is equal to L sub 0 divided by 3 minus K sub s divided by m times L sub 0 times delta t squared, 0, 0. Finally, Part E asks us to determine the new force on the block. To determine the new force on the block, we do the same thing we did in Part B. We must first find the force from the left spring, which is -K sub s times the final position 4/3 L sub 0 minus Ks divided by m times L sub 0 times delta t squared minus the relaxed position of L sub 0 times x hat, with x hat being 1, 0, 0. The force from the right spring is -2 times K sub s times the final position 2/3 L sub 0 plus K sub s divided by m times L sub 0 times delta t squared minus the relaxed length of the spring, which is L sub 0, times -x hat, which is -1, 0, 0, because, like we said before, the right spring is being compressed while the left spring is being elongated. When we add the force from the left spring and the right spring, we find the new net force to be negative k sub s L sub 0 plus 3 k sub s squared divided by m times L sub 0 times delta t squared, comma 0, comma 0. Thank you.